Right, welcome everybody. Good morning here in Waterloo. Welcome everybody to the 5th session of the RQI-Online 2020-2021. It is my pleasure to introduce as our invited speaker for the day, Professor Faye Dowker from Imperial College London. She's going to talk about positivity and composability in a path integral framework for quantum theory. Faye, the floor is yours. Thank you very much.
Thank you. Thank you very, very much for inviting me. And hello to everybody. Good morning, good afternoon, good evening. I send my very best wishes to everybody. I know that it's very difficult for many people at the minute, and I hope that you find, as I do, that our work is a real haven and benefit to us when we feel very constrained and restricted, but at least our minds can roam free and we can connect and engage with each other in the way that we've always done. But it has a, for me anyway, I'm speaking for myself now personally, it has a very particular value and meaning to me now. So it's really hard giving these talks to a screen and not seeing people in front of one. You don't get the feedback that you normally give. But I found that the talks I've gotten the most out of in the last few months have been ones which focus a lot on concepts, conceptual issues, rather than technical details, which can be hard to follow. So I have made my talk very light on technical detail. I'll mention a theorem, a result that we've proved, but I won't go into the details of the proof at all. It's really a talk that's I'm giving to be stimulating and to provide a particular point of view and to introduce you to certain concepts. Now, how do I advance? Good. So I've learned to give the conclusions of a talk at the beginning over many years of experience giving talks. So I'm going to give the conclusions. Hopefully by the end of the talk, you'll understand what they mean more. So I'm going to argue that the Dirac-Feynman path integral is a basis for a framework for quantum theory that is based on the same concepts that underlie general relativity. And those concepts are events and histories. And this framework for quantum theory has been championed by many people, but particularly by Jim Hartle and Raphael Sorkin, who are both researchers on quantum gravity, and that's no coincidence. The measure on the set of possible events that the path integral provides for every system is given in a particular form, and it's given in the form of something called the Decoherence Functional, D, which has two arguments, A and B, which are both events, possible events in the system. And this Decoherence Functional is Hermitian. I'll explain technically what that means, and it's bi-additive. The set of strongly positive systems in this framework, in this world of path integral quantum theories, is maximal amongst sets of systems that are closed under composition. And this is a relative result that's a few years old now, and was proved by Boas and Navasquez. The set of strongly positive systems turns out to be the unique set of systems that are maximal amongst sets of systems that are closed under composition. And that's a newish result that my PhD student, Henry Wilkes, proved. And I would like to argue that it's a good reason to adopt strong positivity as a condition on new path integral theories, for example, quantum gravity. So in 1932, Dirac wrote a paper, I think it was published a year later actually, called The Lagrangian in Quantum Mechanics. And in it, he contrasts the Lagrangian and Hamiltonian approaches to classical mechanics, and says that quantum mechanics was built on a foundation of analogy with the Hamiltonian theory. Of course, he should know. Pretty much everyone associates canonical quantization with Dirac. But there's an alternative. These are all quotations from this paper, from Dirac's paper. Provided by the Lagrangian, there are reasons for believing that the Lagrangian one is the more fundamental. And he gives two reasons. One is that there's no action principle of the Hamiltonian theory. And the second reason is that the Lagrangian method can easily be expressed relativistically, while the Hamiltonian method is essentially non-relativistic in form, since it marks out a particular time variable as the canonical conjugate of the Hamiltonian function. And I would claim that part of our struggles with trying to understand quantum theory in its relativistic form stems from the fact that we are often tied to a canonical Hamiltonian approach, whereas the relativistic worldview is a space-time view, and that does not, it is essentially incompatible with the Hamiltonian method. Dirac showed that the Lagrangian does appear in quantum mechanics, but it appears not in the canonical approach, but in the path integral or sum over histories. And I believe this is a fork in the road where you can decide to take a Hamiltonian canonical path, or you can decide to take a covariant space-time Lagrangian path. So let's take the Lagrangian road. The path integral provides a reformulation of the Copenhagen rules for prediction without Hilbert space. I'm going to say a little bit more about what I mean by that claim. It provides what I would call quantum theory with external observers, but just different from it. You don't need Hilbert space to provide the same Copenhagen predictions and probabilities. It also reproduces the predictions of the textbook theory whilst including the measuring device in the quantum system, something that the Copenhagen interpretation cannot do. So it is a formulation of quantum theory with observers, but they're internal to the system. They're inside the quantum system. And it gives a different perspective on the struggle to picture the quantum world in the absence of observers altogether. So, for example, in the early universe, when we don't expect anything like a classical system, classical observers, classical measuring devices. It avoids what Raphael Sorkin calls the psi rut, where the status of psi, the state or wave function, is agonized over. And it avoids it because there's no concept of psi fundamentally in the path integral approach. The framework is built on the twin concepts of history, so history as in sum over histories, and event. And an event is something that can happen in the system and comprises several histories, all the histories, the fine-grained histories that, all the different ways, fine-grained ways that a particular event can happen. And these two concepts are what Feynman's popular book, QED, which is based on some popular lectures that he gave in the 80s, is based on. So if you read Feynman's book, I don't think he mentions anywhere quantum state. He certainly doesn't mention Hilbert space, doesn't mention wave function. The whole book is based on these concepts of history and event. The amplitudes of histories, to calculate the probability of event, you add up the amplitudes of the histories in that correspond to that event. And these same concepts, history and event, are the concepts that general relativity is based on. So I claim it's not surprising that it is the framework of choice, the path of choice for many workers on quantum gravity. So let me explain a little bit more about what I mean about it doing the job of the Copenhagen interpretation and then going beyond Copenhagen. So I'm going to specialize now just to non-relativistic quantum mechanics, say of many particles or one particle, it doesn't really matter. The path integral gives everything that the canonical theory gives. It gives the probability that the outcome, which I've denoted by delta, of a sequence of measurements, and think of those as position measurements, a sequence of position measurements in time, ordered by time. That probability of obtaining that outcome when this sequence of measurements is actually done by some external apparatus is given by this double, it's actually a path integral, it's a double path integral actually. So this d gamma gamma primed here, this thing, is what I'm going to call the fine-grained decoherence functional. And that is proportional to e to the minus is, that's classical action of gamma, times e to the is of gamma primed. The fine-grained decoherence functional also depends on the initial state. So you take that fine-grained decoherence functional and you sum it, you add up all the histories that correspond to that particular outcome. So all the histories in which the particle does go, is at those positions, the outcome of that of the measurement. And it's a double sum. You sum over gamma in one argument and gamma primed in the other argument. So I'm just going to make that claim. That is a claim completely standard. If you take the usual Copenhagen probability formula for that sequence of outcomes, and you insert the unitary time evolution operator in terms of in its path integral propagator form, then this formula here is exactly what you get. Now, that's a very suggestive formula, and just because you can, you can see that it gives you more information. You don't have to sum gamma over a particular set of histories that agree with some outcome of some measurements. You can, and you don't have to sum gamma and gamma primed over the same set of histories. You can do.
There's a comment from Don Page. Saying, I don't know why, what you mean, Don. I'm going to let you unmute yourself because you said Faye is not showing her screen with formulas. Can you ask her to show? I can see the slides that Don. Is anybody having this problem?
Yeah. I don't know. Maybe is there something is there something I need to do? I'm seeing. Well, it's wonderful to see Faye's face and to see her after it's been a long time seeing her in person. But I assume she's showing some formulas, but I can't see them. I don't know. Do I need to do something different to be able to see
I think Don is the view. Maybe on the corner of your screen there should be something called view, right? A button called view. Perhaps you have changing that will work, because I think we all see the slides, correct? Everybody else.
Okay, view. Let me just wait a minute. Oh, here. Okay. Yeah, let's see.
Does it work?
Here, wait a minute. Okay, I see some equations. Okay, I'll fiddle around and see if I can figure
Sorry to interrupt you, Faye. I wanted to make sure people were seeing the presentation too.
Yeah. I assumed everybody. I'm sorry. It's just my problem. Anyway, sorry.
So my apologies, Faye. Please.
No problem. That's fine. Of course. So. Jim Hartle, I believe, is responsible for this terminology, decoherence functional, which is you take this formula for the probability of a particular sequence of outcomes, and you just do what you're led to do, which is let's sum gamma not over delta, but over any set of histories at all, A. And let's sum gamma primed over any set of histories at all, B. And we're led to this object d of AB. It's a complex number, and you can think of it as the interference. The decoherence function. It's an unfortunate terminology that we're stuck with historically now, but you should really think of this DAB as the interference between the histories in A and the histories in B. In the two events A and B, this is the interference between them. If it's 0, we would say that the two events A and B do not interfere. And the diagonal term of the decoherence functional, DAA, is what Raphael Sorkin calls the quantum measure. So I've just written the formula out again. Now I'm summing gamma and gamma primed over the same set of histories, A. And you can do that for any set of histories. And you can think of the set of histories as being a subset of omega, where I've use this Greek letter omega to denote the set of all histories. So if you're doing the full path integral over all histories, omega would be the set of histories that you're summing over. So the caveat, there are knotty issues to do with defining mu of A and DAB for sets of histories more general than finite sequences of position ranges. And the question of which sets are measurable is analogous to and more problematic than the question of which sets are measurable for Brownian motion, for example. In that, you can solve that problem. You can define what people call the Wiener measure, but that is technical and hard. But in the case of quantum theory, it's even more difficult and even more problematic. But I'm going to sidestep all of those issues by just assuming that from now on, our system is finite. Say space and time are discretized, finite, and we're considering physics on a lattice in a box, say. So we have finitely many histories, and all subsets of the set of histories have a well-defined measure, mu of A. Okay, I claim that we can do more with path integrals than you can do with Copenhagen. Copenhagen requires you to make a split of the world into system and classical measuring devices, but you don't have to do that in a path integral framework. So let's suppose that our quantum system is comprised of the full quantum system is composed of some microscopic system and some measuring devices that are going to make measurements, a sequence of measurements on that microsystem. And it's all together modeled by some n particle system, where n is very big, and there's no external apparatus. It's a closed system. Now, each space-time history, big gamma, comprises n particle trajectories and describes both the measuring devices and the microsystem together. Now, each sequence of macroscopically registered outcomes, and I'm going to call that an instrument event, corresponds to a set of histories X. There are a lot of histories in X because a macro event is very coarse-grained. There are lots of different ways the particles can be behaving with which correspond to the same macro event, the same pointer position. The quantum measure, however, for X is calculated in exactly the same way as with the same formula as before. So it is a double sum, a double path integral over all the histories in X and all gamma in X and gamma primed in X. And then I claim, for all practical purposes, and that's a technical term in the foundations of quantum mechanics coined by John Bell, FAP. So FAP, this double path integral, this number, is equal to the Copenhagen probability of that sequence of outcomes. So FAP means they're not exactly equal, but they're equal for all practical purposes. And this claim, which is justified by heuristics, by decoherence arguments, and by some modeling, is that the claim that it doesn't matter where you make the split between the quantum system and classical measuring device. The probabilities will come out the same, FAP. And nobody that I know doubts this, so this claim. But you can see here that you do not need to divide the world fundamentally between quantum system and classical measuring devices and treat them differently. You can treat them within the same framework, but you can calculate the probabilities of these instrument events nevertheless. Okay, so quantum measure theory is the name that Raphael Sorkin gives to a histories-based framework for quantum mechanics. And Jim Hartle calls almost the same framework generalized quantum mechanics. So as far as this talk is concerned, where I'm not going to go into the interpretational aspects of histories, sum over histories, path integral framework, they are essentially the same thing. They're built on the decoherence functional. And this is an alternative to the canonical psi framework. In this framework, this path integral framework, a quantum system, a finite quantum system, is a set of histories, which could be, you can think of as particle trajectories, field configurations, or even space-times. There is a Boolean event algebra, which is just the power set of the set of histories. So an event is just a subset of the set of all histories. And a complex decoherence functional for all events A and B in the event algebra. And this decoherence functional is Hermitian. So D of AB is equal to D, the complex conjugate of D of BA. It's additive. That means if you have an event which is a disjoint union of two events A and B, then D of it with C is D of A with C plus D of B with C. That is just the superposition principle. It's the fact that quantum amplitudes are additive. There's a condition of positive measure, which is that the mu of A, the diagonal term of the decoherence functional, is non-negative, and it's normalized. So D of the whole sample space, omega, is equal, the mu of the whole sample space is equal to 1. Now that's a little cumbersome to deal with. So for the purpose of this talk, I'm going to simplify things. I'm going to tell you about a mathematical result, and to understand that mathematical result, it's just easier to simplify things down. So I'm going to define now a system to be a pair, omega D, where omega is a history set and omega indexes a Hermitian matrix. So it's just a finite, D is just a finite Hermitian matrix that satisfies two conditions. Oops. If you take the sum of all the all the entries in D, where you sum over the same rows and the same columns, the same set of rows and the same set of columns, that's got to be non-negative for any set of rows. So that's indicated here. So I've got D gamma gamma prime. Those are the entries of the Hermitian matrix. I sum that for gamma in some index set of A, some subset of the history space, and also over gamma primed in that same subset. So it's just, you take your matrix, you take some subset of the rows, you take the same subset of the columns, and you just add up all those entries in those rows and columns. And that's got to be non-negative. And if you sum up all the entries in D, then you get 1. That's the normalization condition. And I'm also going to define a strongly positive system to be one such that its D gamma gamma primed, is a positive semi-definite matrix. So that's a stronger condition than this condition. This condition does not imply that it's strongly positive, but being strongly positive implies this condition. Okay, so strong positivity is a stronger condition than this positivity of the measure condition. Now let's consider composing systems like this. So let S1 and S2 be two systems, and let's compose them in the blindingly obvious way. We just take the history space to be the Cartesian product of the two history spaces, and we take the matrix, the decoherence matrix D1 tensor D2, to be exactly the tensor product of the two matrices D1 and D2. Now, there exist systems whose composition so defined is not a system. That is, the composed, the tensor product decoherence functional is not non-negative on all events. So you can find an event for the composed system so that this decoherence functional term, the diagonal term, is less than 0. So that's a bad thing. We don't want to have one system that you can't compose with another system. It's sort of a general principle that people like, that if you have some physical system, then you ought to be able to compose it with a non-interacting copy of another physical system. However, if the two systems are strongly positive, if their decoherence functionals are positive semi-definite, then the tensor product of two positive semi-definite matrices is positive semi-definite. So what the set of strongly positive systems is what I call tensor closed. So it's a set of systems which is closed undertaking tensor products, taking composition, making compositions, and that's a good feature for a set of systems to have. And what Bose and Navasquez proved is that this set of strongly positive systems is not just tensor closed, but it's maximal amongst tensor closed sets of systems. That means that you take your set of strongly positive systems, then there's no other system that you can add to it and that set remain tensor closed. If you add any other system to your set, then you'll ruin the property that you can compose any systems together in your set. So it's maximal. It's as big as it can possibly be. So that's a nice property too. But that raises the question: are there other maximal tensor closed sets of systems? And the answer is no. And that's in my remaining time, I'm just going to sketch for you the proof of that theorem. So I'm going to formalize all this a little bit. So let's let W be the set of systems. That's history spaces with decoherence functionals. Let a set of systems A be tensor closed if A tensor B, the composition of system A with system B, is also a system for all systems in A. Sorry, that's a stray bracket there. It shouldn't be there. And let's consider a set of systems A. I'm going to define what the Galois dual of A to be A hat, which is the set of all systems such that its composition with any system at all in A, so B is in A, is also a system. So being in W means it's a valid system.
Okay, 5 minutes warning.
Yep, thank you. Thank you. And final definition, a set of systems is Galois self-dual if A equals A hat. If a set equals its dual, then we say it's self-dual. This terminology Galois dual comes because this definition of A hat of dual makes this into something called a Galois correspondence. But I can explain what that is, but it's not particularly relevant for this talk. So let's consider a tensor closed set of systems. That's a set of systems where if you take any two of them, compose them, then that's also in your set. Then saying A is Galois self-dual is saying that A is maximal in that set of tensor closed systems, because it means that anything that you can add, you can't add anything else, and for that system, that set to remain tensor closed. So it's just a more formal way of saying that A is maximal in the set of tensor closed sets. And I'm going to define S to be the set of strongly positive systems. And one can prove that S is tensor closed. It's just the statement that two positive matrices, the tensor product two positive matrices is positive. And I'm going to define another set of systems to be the set of systems which have non-negative entries. So that's just the decoherence functional, that matrix just doesn't have any negative numbers in it as entries. That's also tensor closed, because of course, if you take the tensor product of two matrices, all of whose entries are non-negative, then you get a tensor product matrix, none of whose entries are negative. So R plus is also tensor closed. And we're going to, the proof that the theorem that we proved is that if A is tensor closed and Galois self-dual, then it is S. It's the set of strongly positive systems. Okay, so this is the outline of the proof. You can prove that R plus, the positive entry systems, is not Galois self-dual. You can prove that if you have a system and it's not strongly positive and it's not a positive entry system, then you can take its tensor product with itself some number of times and it becomes not a system anymore. It fails the condition that its diagonal terms have to be positive, have to be non-negative. You can show that a tensor closed set must be a subset of the union of the strongly positive ones and the positive entry ones. Then you can show that a tensor closed set must be a subset of either S or of R plus. You show that a subset of R plus cannot be Galois self-dual. You show that a proper subset of S cannot be Galois self-dual, and therefore if A is tensor closed and Galois self-dual, then it must be S. So yeah, there's a series of lemmas, and the conclusion is that anything which is Galois self-dual and tensor closed must be the strongly positive system. So my final slide, I've only considered finite systems here. The results can be extended to infinite systems. It's a strong argument to adopt strong positivity as the correct physical positivity axiom for a decoherence functional in a new path integral based quantum theory, such as quantum gravity, where the rules are up for grabs, of course. So we propose that we should adopt this axiom there. Also, strong positivity allows a Hilbert space to be constructed. The path integral approach is not based on Hilbert space, but if you have strong positivity of the decoherence functional, you can construct a Hilbert space. And in non-relativistic quantum mechanics, this history Hilbert space actually equals the canonical Hilbert space. And then finally, this is future work to be done. The path integral quantum theories sit at level 2 in a hierarchy of measure theories, with the levels labeled by how much interference there is. So roughly speaking, at level 2, you have a decoherence functional with 2 slots. At level 3, you have a decoherence functional with 3 slots. So there's 3-way interference. And we do not know how to generalize the strong positivity condition to higher level measure theories. And one motivation for this work was the hope that these concepts of composability and Galois self-duality or maximality will be more easy to generalize than the sort of mathematical condition of strong positivity. And I'll end there. Thank you for listening.
Thank you very much, Faye. Clap on behalf of everybody else who's muted. Thank you for the great talk. Your timing was perfect. You didn't bite anything into the question time, which means that we have plenty of time for questions. We're going to operate as usual. If you have a question, use the raise hand feature on Zoom. And if you can't find it for some reason, just activate your video and signal Rick. Rick is going to be watching for you that. But it'd be much better if you use the raise hand feature.
Eduardo, shall I stop sharing my screen or shall I continue to keep the slides up?
It's for now, it's up to you. In case you want to go back to your presentation, it's perhaps
okay. I'll leave it up, but yeah.
All right. Are there any questions from the audience?
I would bet that Don has a question.
Hold on.
He looks like, okay.
We have Cisco first, but Don perhaps, Don too. So I'm gonna, first Cisco is gonna go, then Don, and then Chris, if that's fine. So I'll do, now you can unmute yourself. Cisco, you go first.
Yeah. I was just curious, has there been any progress with dealing with sums over metrics or spacetimes? Or is this still an intractable,
that's a great
non-categorizable?
Oh, that's a very, very good question. Okay, so yes. So for example, there is a program called Causal Dynamical Triangulation, in which championed and pioneered by Jan Ambjorn and Renata Loll and their collaborators. And they are trying to calculate on the computer the gravitational path integral using a regulator, which in principle should be taken away and taken to zero. So they're discretizing the space-times that go into the gravitational path integral, and they've had some success at doing that. So I mean, it's computational. They're doing Monte Carlo simulations of a path integral. They have to do a Wick rotation because so far no one has made much progress on doing a sum over histories where the amplitudes really are, for gravity, where the amplitudes really are complex. So they have to do a Wick rotation, but they are able to do Monte Carlo simulations of their path integral, and they get interesting results. I
remember the earlier results with this approach and causal set theory and a couple of other ones. I haven't seen any of their most recent developments, so I was just curious if they've solved things like uniqueness of the rotation back from Euclidean time, which is kind of was a problem in my mind because of the multiple ways that you can rotate back. It seemed kind of unclear exactly what the Euclidean sum or Euclidean time would actually mean.
I think that's a very important question. I don't think that is solved. I think that's, that remains an unknown. I mean, what the results of their Euclidean path integral mean for real space time. So yeah, that's absolutely fair. I don't know of any developments on that. I mean, to the extent that's a problem, it's a problem for everybody, because yeah, that in the sense that if we're going to actually do numerical simulations of the gravitational path integral, then so far all our technology is set up to deal with positive measure, real positive measure, and the question of how to interpret that, how to rotate back, as you put it, that's an issue for everybody. Yeah, and I can't say that any progress has been made on that.
Thank you very much. I think Greg pointed out that Don perhaps has a question. Is that correct? You should be able to. Oh, not yet. Now you can unmute yourself, Don.
Oh, let me try.
We hear you. We hear you.
Oh, you hear you. Okay. No, I'm very, very, very nice talk. Sorry, Faye, and I'm sorry with my technical not understanding Zoom that I interrupted by saying I couldn't see it. So I'm sorry about that. But anyway, it's great to see you. I just want, you have this mu of A, which is the some positive measure for events. And you say this is that you can get a Hilbert space. So for any positive operator in the Hilbert space that would have a non-negative expectation value, can you construct some corresponding event? I mean, in other words, does this formalism that gives you positive measures, that's mu of A, can that also give positive measures for all positive operators in the resulting Hilbert space?
That's a very good question, Don. And the question is, what do operators in the Hilbert space correspond to? And I think that they correspond to functions on the set of histories. So, for example, momentum at a particular time. So if we just talk in the non-relativistic case, momentum at time t, for example, is equal to some value, then that would correspond to the set of histories in which momentum, you can map a history onto a number, which is, you just read off the momentum of that history at that particular time, but that those properties are encoded in the properties of the history. So the translation between the canonical framework in which you have canonical mechanical degrees of freedom and the histories framework is not simple. It's not straightforward. I mean, if you were to ask about energy, for example, then the energy of a history, that would be something. I'm not sure how you would interpret the energy of a given history. That's that's something that is that's something which is non-trivial, I think. So I think there's a way to interpret different operators, different observables, let's say, in the path integral framework, but it's not simple. It's not straightforward.
Yeah. Okay. Well, that would be nice. I mean, as you may know, I have this conjecture that perhaps there are a fundamental set of observations, which in my mind might be conscious perceptions, and each one in the sort of canonical form, each one has a positive operator associated with it, and then the measure for that observation is just given by the expectation value of that operator. you know, in the quantum state of the world. And so, you know, I guess if one could do that in a path integral approach, then that, you know, that would be great. You just say there's certain positive probability that the path integral thing gives, and you could use that as a measure for different observations, and then, you know, then do anthropic sort of things like observation selection things, asked with the probability of an observer seeing the fine structure constant less than 1/100 versus the probability of it seeing the probability greater than 1/100. You could test theories if you could have these measures for different possible observations. So it'd be nice if that could be also expressed in the path integral formalism.
Yeah, I suppose I'm ambivalent about whether or not we would want to show that everything you can do in one framework you can do in the other. I think, I mean, in fact, I think that that's probably not the case. I think there are different frameworks which, you know, which are suited to different things, and in the end, I think we'll have to choose between them. So I think it will be a genuine choice. I don't think it will just be that it's a matter of perspective. No. At least that's how I feel about the path integral.
Yeah. Well, if you could get enough measures for things that we might consider to be corresponding to observations, like, you know, if I say that what I'm now consciously aware of depends on something about the state of my brain, for example, then, you know, I mean, I might guess that, okay, that there's some positive operator associated with some configuration and or momentum, whatnot of what's going on in my brain. But of course, if you could also do that in terms of probabilities, in terms of some events or whatever in the path integral, then that'd be fine. You know, it'd be nice to be able to do it either way.
Yeah, you have to take the point of view that anything that you want to discuss has to be describable as a property. So you have to say that if you want to talk about perception, then you have to say that the event of you perceiving something has to be translatable into a statement about the histories and the sum over histories. So there has to be some pattern of events related to each other in some way, located in space, in the region of space-time that corresponds to your brain. So if you can do that, I mean, if you can translate the event that you're interested in into statements about the histories in your sum over histories, then the path integral will provide a measure for that event, a positive measure.
Right. Anyway, excellent talk. I really enjoyed it.
Thank you. Nice to see you, Don.
All right, thank you very much. Next question from Chris Fuster. Chris. Yeah.
Thank you. Thanks very much, Faye. Could you say something about your results on infinite systems?
Yes, I can. So let's go back to blah, 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 blah. Right. So in the infinite systems, you have a set of histories again. The event algebra is not all of the power set, but it's just some. The events are subsets of omega, but they're not all of them. And then the definition of the decoherence functional is as it is there. It's for all of it's now you have a DAB for all events in the event algebra. The simplified definitions are used here. You can't really use those anymore because D of gamma gamma prime no longer exists really, you know, because it's zero. So when you have infinitely many histories, then, you know, the fine-grained histories, you know, have zero measure. So you can't talk about this sort of fine-grained decoherence functional D gamma gamma prime. You have to always work at the level of DAB, where A and B are the events in the event algebra. But you define strongly positive system then, not in terms of this fine-grained D gamma gamma primed, but you say, take any finite collection of events. Let's say there are n events in your finite collection, and I form a matrix let's say they're A1, A2 up to AN. I form the matrix Dij, which is D of event AI and event AJ. Yep, and that has to be a positive matrix. And that's true for any finite collection of events. That defines strong positivity in the infinite case. Then you have to define what you mean by composed system. So in fact, the composition law is this one. It's that the Cartesian product of the histories of the history spaces is the composed history space, and you define the composed decoherence functional as the tensor product of the two decoherence functionals. And the rest are the same, but you have to always rely on the strong positivity of the positiveness of this finite matrix, where you evaluate the decoherence functional on this finite collection of events. So it's a little more, you just need to do more work because there's a lot more to consider, but the essential aspects of the proof are the same. You go through the same set of lemmas that you need to prove for the infinite case.
So it's somewhat similar to the way you identify the fact, if you're looking at a Fourier transform of a positive function, there's a similar way of identifying that by looking at matrices and looking to see that those are semi-definite. Was this part of the thinking in the proof, or am I just barking up the wrong tree?
No, I think that's right. That's the right way to think about this condition. It didn't play a role in the proof, as I remember. So maybe if you think about it in a particular way, you can see that that's there behind them. But yeah, we didn't think of that in developing the proof. So
Right.
Yeah.
Thanks very much.
Thank you very much. I see no more questions. I have a little question, way more innocent, I hope, than the previous ones. So in this formalism, what would be the equivalent? So in this formalism, you're treating measurement apparatuses on equal footing, let's say, as the systems, right? In that particular way, what would be the equivalent to the Copenhagen Luther's rule, right? I mean, this quantum to classical transition, as in eventually from those measurement apparatuses, we're going to get a value out of a measurement. Somebody does something in the lab. What would be the equivalent to that update rule, whatever that is, right? In this kind of formalism, how do you incorporate the information that an experimenter knows that the outcome of a measurement is 42, for example?
So remind me what the Luther's rule is.
Sorry, Luther's rule is just a state updates, right? As in like when the Copenhagen typical view, which of course is not great in many ways, is saying that when we have a quantum system, we make a measurement with a measurement apparatus, and now we update the quantum system with the knowledge that we have out of the measurement. So this quantum to classical transition.
Yes. I probably wouldn't call that the quantum to classical transition, but I do understand what you mean. So if we go back here.
Not in the sense of something macroscopic becoming classical, but in the sense of getting a definite value.
Yes, right. So if you only restrict yourself to these instrument events, then these mu's here are probabilities. So they're probability distributions. They obey the Kolmogorov sum rule. They behave like probabilities, and you can make predictions in the usual way, let's put it. And because it's a probability distribution, you can consider conditional probabilities. So you don't need, so the concept of collapse of the state or the updating is just a matter of conditioning on past events, say, that have already happened, and and then you just you can ignore the rest of the sample space because you're now conditioning on a particular macro event. So the updating is just a matter of considering this mu of, so suppose this X is a whole bunch of outcomes, a whole bunch of different measurements, some of which may depend on the previous ones, whatever complicated thing you like. But so long as they're actual instrument events, this will be a probability distribution. And then you can simply condition in the usual way that is familiar. So it's, there's no kind of weirdness there. There's no collapsing, for example. Does that
no state update, rather a conditioning of probabilities to knowledge that you have, right?
Yes, it's conditioning. Yeah.
All right. So yeah,
or it's conditioning not on knowledge, but on what has happened. So if you want to depersonalize it,
yeah,
you could just say things have happened, and the probability distribution is conditioned on that.
Right, and you could define something happened as, the outcome of some measurement was 33, and
Yes.
you can condition that.
Yes, you can. Once you have this mu of x, you can, and part of x is that a particular outcome is 33. Then you can condition on that.
Thank you very much. Thank you for indulging me. There's one more question that Suad, but I'm inclined to accept it. So Albert.
Yes, thank you. It's a very short question. It's just a basic point I think that somehow may be missing. So can you explain, the crucial concept here was this definition of strong positivity, having this strongly positive system or measure. But the fact that the measure was always positive for any event. So can you elaborate again that on the difference between the fact that the measure is supposed to be positive for any event and the notion of strong positivity, which presumably is stronger? Because somehow naively one might have thought that the two are kind of equivalent, at least for finite systems maybe. Or so what am I missing there?
Yeah, good. So this mu of x, so the condition
I mean in the general case when you were defining strong positivity.
Okay.
Here, yes, exactly.
Yes. Okay. So one question is why should this be positive? Okay. So we can question anything.
No, but that's
the rules
fine.
of the game. But let's accept that. Right?
Yes, that's fine. But then I just wanted to understand what makes the strong positivity condition stronger than that. Because if that, the first thing you highlighted, should be positive for any event A, why does that have less information than the strong positivity?
Okay, so let's think about what strong positivity, one definition of strong positivity is that if you take a let's say that D is an n by n matrix. Take a vector in Cn, call it V. Then V dagger dV has to be greater than or equal to 0 for any V. Right. But if you look at this condition here, this one, the positivity of the measure condition, what is that? That is the condition that if I take a vector V, which has only zeros and ones as its entries, then V dagger dV is greater than or equal to 0. So positive semi-definite means that V dagger dV is greater than or equal to 0 for any complex V, but this positivity of the measure condition is only true for what I call binary vectors.
I see. Now I understand. That's the subtlety that I was missing. Okay, thank you. I understand. So the point is that the first one is weaker because it only applies to binary vectors. Okay, thanks. That was the point I was missing. Thank you.
All right. Thank you very much. We ran out of time, but we're very well employed. Very nice talk, Faye. Thank you very much, and thank you very much, everybody. Let's thank Faye again. Great talk. And we're gonna have the next talk. I'm gonna pause the recording while the next speaker prepares.
It's 20 minutes.
All right, so the next speaker is Nicolas Funay. Well, Dr. Nicolas Funay. That's gonna talk about, recently used to be a PhD student at the University of Waterloo. Now, Dr. Funay is not anymore a student at the University of Waterloo. He's going to talk about causality violations in cavity quantum fields. and in particular about the rotating wave approximation. So Nico, the floor is yours anytime you want.
Thank you, everyone. Thank you to the organizers and also to the participants to make the conference possible. So I'm going to be talking about causality violations in quantum fields. Generally, which these are problems which arise when you start using approximations, and we'll be focusing our attention on the rotating wave approximation as a whole. So if we have start with what are the approximations? Let me start that again. Let's start with the standard interaction model, the unit model, which we are all comfortable with. In this case, we'll be writing it out as chi sigma x tensor with a smeared detector, smeared by a function f of x and phi. And the rotating wave approximation effectively asks us to expand the field operator and the sigma x operator on the qubit and into this format here seen on the last equation. And then I'm going to color code the first two terms in blue and the second two terms in red, and I'm going to call the blue terms co-rotating terms and the red terms counter-rotating terms, on the basis that the blue terms oscillate slowly because they depend on a difference of frequencies, as you can see, omega minus capital omega, and the red terms depend on a sum of frequencies, omega plus capital omega. So these red terms will, on the whole, be expected to oscillate more quickly in time. Plus, the rotating wave approximation asks us to eliminate these red terms and just leave us with co-rotating terms. And the nice thing about the rotating wave approximation from our sort of high school classical pictures of spectroscopy is that it's excitation preserving. So the annihilation of a field excitation results in the excitation of the detector and vice versa. Now, generally speaking, we all assume the rotating approximation is good for long times. And the basis of this belief is when we study excitation probabilities in the long time limits. So if we consider, for example, the probability of exciting a qubit, a detector from the ground state to the excited state, then the general equation for the full model is given by this equation here. And we can see that as time goes to infinity, the second sort of time interval, both time intervals give us our delta of the sum of two positive numbers. So it goes 10 to 0. And of course, given that these two terms are in red, the rotating approximation will give us 0 anyway. Conversely, when we consider the probability of vacuum emission, so a detector de-exciting and emitting an excitation, then the two theories coincide exactly. So rotating approximation, based on this, we generally assume the rotating approximation gives us exact transition probabilities when for long time limits, so T omega much larger than 1. Within this talk, we'll show both with and without cavities that the rotating approximation, despite this idea that the rotating approximation works well for long times, we're going to show examples of the non-locality that rotating approximation introduces and causality violations which persist despite this, despite going towards long times. We'll also be discussing a stronger criterion which should be used when considering using the rotating approximation. And we'll also be introducing a numerical trick which you can use in rectangular cavities so as to reduce the need for the rotating approximation and single mode approximations. So is the rotating wave approximation any good, for starters? If we look at the interaction Hamiltonian itself, this A sigma plus A dagger sigma minus business, we find that we cannot actually express the interaction Hamiltonian in terms of local operators. So we can't really write it out in terms of some linear combination of phi and pi smeared only in the same way as the initial detector. So instead, when we actually try and work out exactly what it looks like in terms of local operators, we end up with half of the initial interaction. And added to that is a sigma y contribution tensored with something non-local, something which has been smeared with this 1 on x minus y squared non-local kernel. So what that means is that that has turned what is originally something sharp and non-local, like the unit width interaction with a somewhat local smearing, into something highly non-local, as in the rotating approximation. So that's the interaction Hamiltonian itself. What about actual physical observables or field observables? So to that end, we're going to be considering here for our smearing of the detector, and we're just going to be using a sudden switching for the interactions switching. We'll use these sort of very sharp functions so as to have very clear lines as to where the limits of causality are. And we'll just be using second order perturbation theory starting in the field ground state and the detector excited state. So to that end, we can have a look at what the energy density expectation values are. This vertical line indicates the extent of causal, the light cone, sorry, of the interaction. So we would expect that no energy should propagate beyond the light cone, which is what this graph actually shows us for the exact model, the causal model. Whereas if we compare this to the rotating wave approximation predictions, we find that we do in fact get leakage outside of the light cone, and this leakage decays polynomially outside the light cone. And this non-locality here persists despite the fact that we are in what we would consider to be a long time limit with omega t equal to 600. So it's reasonable to say that that is much larger than 1. So should we be using the rotating wave approximation to consider field observables? So if we consider the equations for the amplitude squared field amplitude expectation values, we can sort of decompose the functions, the equations, sorry, into blue terms, ME1, these terms which depend purely on co-rotating terms, and in red, ME2 terms, these ones which contain counter-rotating terms, so terms which should not exist under rotating approximation. And whilst it may not be entirely clear exactly what's happening, one of the things which make the ME2 terms persist and give us resultant tails such as what we see in this graph here is the fact that this time integral, this double time integral, is usually considered to converge to delta functions of sorts, without considering what happens to the exponentials which multiplied on the outside. So there's this idea that we assume that there's uniform convergence in these integrals when in fact there isn't, and that causes these issues to arise when these x values in particular here are very close to the light cone. So diagrammatically, what that means is if we consider using the rotating wave approximation, we should consider looking at the shaded gray areas. So this is sort of a light space-time diagram indicating a sudden switching on and off for the interaction times. And so what we want to do is we want to stay away from the light cones which are created at the moments the detector turns on and off, because as we know, sudden switchings usually have fairly strong effects on the effects of the field. And then if we stay within the bulk of these regions, within the null-like regions or in very, very space-like regions, space-like regions or very, very time-like regions, on the whole, we would expect the rotating wave approximation to be more or less good. So let's instead consider a communication setup where we'll consider 2 qubits, and we'll also have hard spheres and sudden switchings, as you can see from this space-time diagram. What we'll be doing is we'll be trying to have Alice communicate to Bob via a fairly simple protocol introduced by Waterloo a few years ago. And what we'll be doing is we'll be moving Bob around to see exactly what the communication capacity is. So this is sort of what we get when we consider the channel capacity for the non-approximated model. This vertical line here indicates the boundary between time lag and null lag communication. And this boundary on the right indicates the boundary between null lag and space lag communication. And it's not a very remarkable diagram, but on the whole, we see that we don't have any time lag communication, nor do we have any space lag communication. If we compare that to the retaining wave approximation model, we can see fairly substantial leakage into the space-like communication region. So we have superluminal communication decaying as 1r squared. Also, we have a fairly unusual, unrecognizable, let's say, behavior within the null-like region. Unfortunately, in this case, omega t is not much larger than 1, and that is one of the reasons why it looks so different to the unapproximated model. So summarizing how the rotating approximation works in non-cavity cases, we find that if we use sudden switchings and sort of solid spheres, we can actually compute that the energy density non-localities, the energy density causality violations decay as 1 on x to the 6, and similarly the channel capacities superluminal communications decay as 1 on d squared, where d is the distance between the qubits. So we have polynomial violations of causality when from outside the light cone. This decay rate is independent of t. So retaining wave approximation doesn't always work for a long time. So we should always keep some sort of this diagrammatic idea in mind when we consider where we would be using the retaining wave approximation. Effectively, in situations where causality is not a primary factor. When we consider cavities, the situation changes slightly in the sense that instead of dealing with integrals, we're dealing with sums in our definitions of field operators. And the main difference between that is that the integrals are easier to use. But there is this sort of intuition, which at least I had when I started this project, which was that because we have discrete sums of retaining approximation, or the few mode approximations, the single mode approximation should work a little bit better in cavities. And so we want to see exactly how this intuition work plays out. So similarly, to the non-cavity case, we can decompose the unit derivative interaction, sigma x phi, into co-rotating terms and counter-rotating terms. And once again, apply our rotating approximation by eliminating the counter-rotating terms. And we can then try and put it in terms of local operators, which gives us, again, half of the original interaction minus sigma y times, again, some sort of integral of pi over some sort of non-local kernel. And unlike in the non-cavity case, we can't directly evaluate what this non-local kernel is because we have a sum and not an integral. So some people in the past have tried to evaluate this sum by looking at the small distance limit. So when considering x and y close together compared to the size of the cavity. And in that case, you can interpret this sum as a Riemann sum and then just evaluate it as an integral, which gives you exactly what we got for the continuum case. So effectively, this is what happens when considering distances so small that the boundaries are virtually irrelevant. So to overcome this little issue, we want to see exactly what happens to this non-local kernel when you can actually feel the effects of the walls. And to that end, we introduced this numerical trick. This trick which we developed that allows us to get rid of the omega, which is stuck in the sum here. So we replace this omega with this integral. And in this sense, it turns what is originally an oscillatory and slowly decaying series into what is now an integral and then a geometric sum. So a sum which we can evaluate directly. using this formula here in terms of delta functions, in terms of the Dirac delta comb, and then it gives us something which we can now evaluate, which decays slightly faster. The basis of this numerical trick really comes from the fact that if you simplify the integral in terms of spherical coordinates and integrate out the angular coordinates, you end up with an infinite integral, which you can then interpret in terms of contour integration by adding this little semicircular component, which doesn't contribute to the integral. And this interpretation then allows us to modify exactly the integrand in question so that we may introduce additional tricks when necessary. So the second trick we introduce is based very much on the first one, which is to look at the Whiteman function and note that despite our efforts, this still is a slowly decaying series. So we would like to replace it with, we would like to sort of improve on this numerical trick by changing the integrand here. And to that effect, we replace these fractions with 1 over hyperbolic sines. So that has the benefit of sharing the same poles as this fraction. But then because there are extra poles involved in the hyperbolic sine, we have to introduce a sort of counterweight term on the right-hand side to make sure that everything is accounted for. And this then allows us to write the Whiteman, this monolithic kernel, sorry, in as a more quickly decaying function. So now it's going to be exponentially decaying. And we also have to account for this additional term, which is also exponentially decaying. Now this factor delta here is just—
5 minutes warning, Nico. Yeah.
Sorry?
5 minutes warning. Sorry.
5 minutes, yes. So this delta function is simply a parameter, a numerical parameter. It doesn't have any bearing on the exact, it doesn't affect the results, but it's just a numerical parameter which you can choose, which you have to counterbalance because increasing delta will make the first series decay more quickly, but it'll make the second series decay more slowly. So that just becomes one of the juggling acts, which is common in numerical analysis. So when we evaluate what this non-local kernel looks like, if we put our detector at the position 0.3, then initially this non-local kernel decays at 1 on r squared, as we would expect, and then it sort of finds its way to decaying to 0, as also we would expect from the Dirichlet boundary conditions which we imposed. So now we would like to see once again what effect this has on communication. So we're going to use the exact same setup as we did in the non-cavity case. And this is sort of what we look like. So on the left-hand column, we have omega equal to 9.02. So effectively, that means that omega t will be on the order of 0.9. Alice will be at s is equal to 0.4. And then the first set of vertical lines indicate the time-like, null-like boundary, and the second set of lines indicate the null-like, space-like boundary. So the causal limits, really. And so when we look at the rotating wave approximation, we see substantial leakage into the superluminal communications. We also see substantial amounts of time-like communication. And generally speaking, comparing these two diagrams on the left, they don't really seem to be much alike. You wouldn't recognize the rotating wave approximation diagram as corresponding to the unapproximated diagram further up. On the other hand, on the right-hand side, we have omega equal to 871. So that means that omega t is about 87, which is reasonably large compared to 1. And on the whole, if we look at just simply the null-like regions between 0.6 and 0.8, for instance, the curves look more or less the same. You could be forgiven for confusing one with the other. If we look at the rotating wave approximations on the right-hand side, we still have a small amount of leakage, relatively speaking. Then we have a little bit of time-like communication with a few artifacts coming from the fact that we have a little divergence as 1r squared in the middle. But also, rather importantly, we have that if we look at the peaks of the channel capacity in the RWA, this is about a half of what it is in the unapproximated case. This is a consequence of the rotary approximation eliminating a potential avenue for communication, really. So it's, the RWA doesn't allow a certain process consisting of vacuum excitation and then a reabsorption, which is possible in the unapproximated case. So once again, as in cavities, we have to keep this diagram in mind with the additional constraint that cavities are bounded. So we have a certain limit as to where X can be. And this is usually where our interpretation, where our initial ideas of rotating approximation in cavities comes from. It's that because they are bounded for long times, we can imagine a vertical line starting from somewhere on the diagram around here, you will eventually reach this gray area at the top. So you can sort of soften the criteria for cavities by saying that for long times it will eventually work because X is bounded, and so you have a certain degree of uniform convergence within that subset of X. And strictly speaking, if we return to our first trick, we can see that this non-local kernel actually takes the form of the non-cavity case if we interpret the second series of delta functions as a sum of even number of reflections minus odd number of reflections taking place. So the mirrors behave very much as we would expect them to. So in summary really comes down to that the rotating approximation doesn't work well near light cone boundaries, so near the boundaries of space-like and null-like and null-like and time-like. Because cavities are bounded, the rotating approximation generally works a little bit better in cavities, although you still have to keep in mind the exact space-time regions where you should use it. Our introduction of this numerical trick allowed us to compute cavity mode sums without requiring few mode approximations, without suffering truncation errors, or without having to delve into monumental computer calculations. And so we found that this careful treatment allowed us to compute these desired quantities in a reasonable amount of time. However, one thing we would like to bring to attention is that, as we saw at the beginning of the talk, when we look at the rotating wave approximations predictions of a single detector exciting or de-exciting, in the long time this becomes exact, and that's a result of those probabilities coming from first order Dyson contributions. However, as I pointed out in towards the end, when you consider 2 qubit communications, the channel capacity becomes exactly a half when you use the rotating approximation versus the non-approximated model. And this is a result of them coming from second Dyson contributions and the rotating approximation eliminating one of the population. So whilst the rotating approximation works well, you have to keep in mind that it's inconsistent in the sense that you get exact models at some point, exact predictions in some point, and half of the exact predictions in another point. So whenever the rotating approximation is used, you must be careful, but on the whole, if you stick to the space-time diagram, you should be okay. Thank you for listening.
Right. Thank you, Nicholas. Thank you on behalf of everybody. Now, as usual, we're going to take questions. If you can use the raise hand feature. If not, try to signal Rick somehow. Okay, Rob has a question. Let me just allow you. Oh, you can unmute yourself. Yep.
Yeah. Okay. Yeah. Thanks, Nico. I'm just like I see you've shown that space-time diagram picture several times, and what I'm wondering is, I understand it's symbolic, but what what sets the different scales? So for example, I'm safe if I'm in the triangular gray regions at the left and right, correct? For causality?
Yeah.
Okay, so what sets the distance between that dot and where that triangle begins? And conversely for the other regions, like what kind of things set those scales?
No, I would argue that you'd probably have to be considering relative sizes. So it would what would set the scale really is, for example, the size of these peaks and how willing you are to then introduce small errors. So I don't think there are any specific physical parameters you can look at. It'd be more along the lines of you need to compute relative errors and then what you're comfortable with, I suppose.
Well, I guess I would have thought it would be some property of the detector, and I agree, some error tolerance, right? So, I mean, maybe I can live with a bit of causality violation if I still get the answer I want. I mean, that's the kind of thing I'm curious about here.
This is the best I could offer you here, I guess. This is the amount of causality violations. So if you increase capital omega, for instance, then that should improve the situation. If you decrease lambda, it should improve the situation, although decreasing lambda will also decrease the total value of t, so the relative error won't go down.
Yeah, that won't help. Omega, I guess, that's the gap, right? That will help.
Yeah, so increasing the energy gap looks like the only thing that helps right now.
So if I may say, Nico, I think it's a bit misleading, in my opinion, to present it like that, right? Because that figure that you have is not that the model works on the gray areas. You're saying that the causality violation is not huge in those areas, but in the gray areas that you have on the space-like region, you have short times. In short times, it's not going to work. It's going to give you the wrong answer. Perhaps it's not violating causality too much, but the model is going to give you a very different answer than the full model for short times. Am I not right?
Yeah.
Right. So these areas in gray are not representing when the model is right, where you should use the RWA. Is rather when the violations of causality start not to be too bad, right? If you put the detectors very far away, sure, the tails, the polynomial tails are not going to affect them too much, right? That's what you mean, no?
Well, I'm just saying, I think it should be those scales should be somehow quantifiable.
Yeah, they are.
That's what I'm asking, right? I mean, I see the graph show you're in trouble in certain places, but there's got to be something that sets those scales somehow, I would think.
So just one remark from Albert in this respect, maybe, but I would have naively thought that one way of trying to think about that, besides of course doing detailed calculations, comparing, quantifying, and so on, is that, for example, in this diagram, along the time-like direction, the t-axis here, somehow, as you showed at the very beginning, one would expect that the scale would be something related to a factor of inverse capital omega or something like that, that would set the scale along this vertical direction. And then these schematic pictures you have for the gray areas, if one tries to sharpen that, presumably I would expect that what you have is actually things like hyperbole, that would correspond, to the Lorentz invariant sort of hypersurfaces here, or this hyperbole, which are Lorentz invariant, invariant under Lorentz transformations. So I would expect that, for example, inside the light cone, this triangle, and then the ones outside the light cone, that you can do something like that, get a natural maybe time scale or a spatial scale, for example, something like a inverse capital omega, and then instead of a triangle, I would expect that you have something more like one of these hyperbole that are invariant under Lorentz transformations, and probably similar outside the light cone, where maybe then the scale there has to do the spatial scale with the size of the smearing of your detector or something like that. And then the rest would be determined then by Lorentz invariance. Inside the two detectors, these regions here, I guess you would also need the combination of time and size of your detector. But again, I would try to construct that with objects that are Lorentz invariant. So I think that that might actually help you to define more precisely, at least qualitatively, then the exact values, of course, of these vertices, that will be up to the precision that you want to keep things. But, intuitively, I would expect that they would be related to things like inverse omega or the size of your smearing function. I mean, the support of your smearing function.
Well, that makes more sense, yeah. But this is just a sketch. I think the triangles are there just because it's easier to draw.
Exactly, that would be trying to elaborate on your sketch, yes.
Yeah. So the thing about it is, if, how's the best way to put this? If, for example, you pick X to be a proportional to T, so if X is, for instance, 0.9 T, which would put you somewhere inside here, as T goes to infinity, you will start to converge. Your rotating approximation predictions will start to converge to the standard, the unit width standard predictions. So this gray area really should be a little bit bigger in you would argue, but it's then a matter of how long you're willing to wait, how accurate you want to be, and things like that. So that's why I wanted to sketch in as general and as vague a way as possible.
So Albert, I don't know if you still have a question.
No, it was just this, basically this remark. So,
and I fully agree as well with the remarks you made. Yeah. Okay, we have Rob also. I see that the hand is down, so I assume that also Rob is done. We have Jorma.
Hello, thank you very much. Could you put back up overhead 25? So the formula at the bottom has PV. How did the PV get there?
Oh, technically there probably should be a PV here as well. The principal value comes about because in this formula here,
I think the problem is that you're mixing two different regularization schemes.
I'm mixing two things there. I'm sorry. That actually, that's a typo. It shouldn't. The PV shouldn't be there. It makes no difference to put the PV there or not really.
Thank you.
Really good catch with Jorma. Are there any more questions? Albert, I don't know if you spoke.
yeah, it was just along these lines, but since it seems that Jorma is satisfied. Yeah.
Okay. Okay, are there any more questions? All right, if there aren't, maybe just one more thing, Nico. I believe, though, that is a bit confusing to talk about the model being correct in the gray areas because of the parts that you have. In those gray areas, there's going to be parts that the model is incorrect.
Maybe I didn't say the right word. It's not correct. It's just workable, you could say. Okay. If you're, for instance, looking for channel capacities, you can introduce the correct renormalization of to make sure that you get the right values, and then you can sort of make it work.
Well, that's something to discuss offline, maybe. But this is the scheme. My issue is only with the scheme that you have rather than the results. All right. If there aren't any more questions, then let's thank Nico again. Thank you very much, Nico, for the great talk. And let's proceed with the next speaker of the session. Hopefully the other Nico, it's okay. As usual, we're running a little bit of a delay, but that's the philosophy of this conference. Let's give enough time for everybody to ask their questions if it's possible. If the last speaker has any trouble and needs to go earlier, please do let me know, and I'll try to make it work so that they can stay. They can do it in time. All right, so the next speaker is Erickson Choa. Erickson, maybe you can try to share screen. I'll stop the recording. Right, so the next speaker is Erickson Choa, who's a PhD student at the University of Waterloo. He's gonna talk about what makes a particle detector click. And as usual, Erickson, you have 20 minutes. I'll give you a warning after 15 minutes. And floor is yours.
All right. Thank you very much for the organizers of RQI, and it has been a series of very nice talks until today. So for this morning, I will talk about a project that is still about particle detectors, but it will be on slightly familiar code / unfamiliar side, depending on what your expertise is. So I will talk about what makes a particle detector click in the context of interactions with Fock wave packets. This is what I mean by familiarity, because it seems like there will be a lot of people who might have seen Fock wave packets before. So in particular, I will talk about how Unruh-Dewitt detectors and its quadratic variant interact with Fock wave packets, and how the presence of cavity walls influence detector response to these wave packets. Now, these two things are separately studied elsewhere, but they are not really studied in one place and being compared for the reasons that I will outline in the next few slides. So first, we'll consider something that is a little bit different from quantum optics setup, in the sense that we consider two-level system in Minkowski space with massless scalar field phi, which means that this is basically a setup that is adaptable to relativistic motion. And traditionally, this is what we call the Unruh-Dewitt model, up to modifications with the detector's spatial extent. So if the detector is linearly coupled to the field, what we mean is that the monopole operator of the detector is coupled directly to the first power of phi. And in general, in flat space, you can add modifications to account for the detector size, how long the interaction is going, and mu is basically the analog of dipole in electromagnetism. However, you can also consider quadratically coupled variant, where you, instead of coupling the phi, you couple it to the normal ordered phi squared of the field. This kind of coupling is common when you consider, for example, in fermionic type of interactions, where the underlying field is a fermionic field. As some of the Unruh-Dewitt detector talks have shown, essentially, if you want to compute the excitation probability or transition probability of a detector, it boils down to something that appears of the following structure. So it will involve space-time integral over how long you interact and the size of the interaction region, which means the size of the detector involved, and also the energy gap. But more importantly, it involves the Weigmann two-point functions of the field, and it depends on the state of the field you choose. However, if you put a quadratically coupled detector, the answer is the same, except that the two-point function is no longer what is traditionally called the Weigmann function, but is the product of the normal ordered square of the fields. So this normal ordering is necessary to basically remove the kind of tadpole divergences you see in interacting field theory. So these two equations alone basically tells us that up to some choice of your interaction time and size of the detector, essentially the main task boils down to computing the two-point functions of the field. And that depends on what state you choose. And for this purpose, let us consider one particle Fock FT. So we really want something that corresponds to a state which has a one particle excitation with frequency, say, omega. For massless field, it corresponds to modulus of the 3 momentum. However, we know from standard quantum mechanics that this kind of definition do not work because it is not a normalizable field state if you are considering a Minkowski space or any space without cavity walls. Well, the standard solution, which there are probably 100,000 papers out there that use this, is that you put finite bandwidth. Okay, so by that we mean we consider wave packets instead. So around k0, we will smear the momentum space with some functions that corresponds to the wave packet that we consider. So more specifically, that means we write something like this. We write one particle state to be basically the creation operator smeared with some function that is L2 normalized to unity. This is basically the requirement that the state is normalizable. Now, for convenience, we choose f, the smearing function, to be something that has a peak around the k0 that we intuitively think as the frequency of the wave packet, as the dominant frequency of the wave packet. Now, this is kind of important to say because if you look at the normalization condition, actually one particle Fock state has nothing to do with having just one peak, right? You can have 100,000 peaks in your momentum distribution, but it still corresponds to one particle Fock state. And that's because really the definition of one particle Fock state should be one who is the eigenvalue, who is the eigenvector of a number operator with eigenvalue 1. And with this in mind, we can now proceed with the standard calculations of Unruh-Dewitt detectors. So it boils down to computing the Weigmann two-point functions of the field. And it turns out that it is a very general feature of Weigmann functions of arbitrary states that you can break it into the vacuum contribution, which is the distributional part, and also the non-distributional part that depends on the excitation of the field, which means it depends on the function f. And what it boils down is that the detector response that you compute will also split by linearity into the vacuum part and the non-vacuum contribution. And what's nice in relation to Nico's talk previously is that this non-vacuum part would be what we usually call the co-rotating part and a counter-rotating. So this is a counter-rotating part and this is the co-rotating part. And you can see this from the fact that there is a term that is a Fourier transform of the interaction time, the switching function that goes with a plus minus of the energy gap of the detector. In what follows, we are going to make some assumptions that is really purely for concreteness and simplicity because we want numbers, right? So one, we'll make the assumption that the detector is point-like, so the smearing will just be a delta around the center of mass. We'll also make sure that the detector is switched on adiabatically for a very long time. That means whenever it is possible, you take this to be a constant number 1, but otherwise you take this to be a Gaussian, integrate everything first, and then take the limit t goes to infinity. This is the equivalent to taking adiabatic limit. And then finally, we are going to make a precise fixed choice of the Fock wave packet so that it looks like a Gaussian. And this is the form of Gaussian that is commonly used in the literature. Now, the nice thing about those approximations is that the vacuum contribution will drop because of the long time limit. This is a well-known result since Birrell and Davis textbook, for example. And also this, the counter-rotating part will also drop out. So after this limit, the long time limit point-like regime will basically reduce to just the co-rotating term. So this is, and the choice of the Gaussian Fock wave packet essentially allows us to even compute this whole transition probability exactly in arbitrary dimensions in terms of modified Bessel functions. Now, there's one thing I should mention with relation to Nico's talk is that the long time limit in this calculation shows that single mode approximation and rotating wave approximation is in some sense the same thing, right? It's basically just a long time limit. And this is the first result that we found. Okay, so what we found here is that there is something peculiar about the phenomenon of resonance, right? Because in this case, what you see is that detector, as you vary energy gap of the detector, the transition probability peaks at the expected place, which is the peak of the wave packet. So this is what we usually tend to think of as resonance. But what is peculiar here is that the behavior of the peak as you make the as you vary sigma here, so the sigma is the size of the wave packet, and you realize that as sigma goes to 0, when the sigma gets smaller, which corresponds to a more monochromatic wave packet, different dimensions behave differently. So in one dimension, you see that the transition probability increases as you make it more monochromatic, but in 2 dimensions, it turns out that it approaches a fixed constant. And then after you go in 3+1 dimensions or higher, this model shows that the transition probability actually drops in the monochromatic limit, which means that as you make the wave packet more and more tight in frequency, the transition probability actually goes to 0, even though for any fixed sigma, you always see an obvious peak that declares that it is a resonance. Now, the problem is that is significant because this is not what happens if you redo the exact sum calculation in a cavity. So if you redo the same calculation in a cavity, these expressions are basically the expression you get when you replace integrals with sums. And you replace the modes from plane waves into a standing wave when you put them in a box of dimension L. And the Fock wave packet now has to satisfy normalization based on sums. So that means the sum squared is the modulus squared of the sum is going to be 1 instead of the integral. And if you choose the same Gaussian, it means that the normalization will now be not the same as the continuum one, and the proper limits will go to a Kronecker delta instead of the Dirac delta function. So this is one of the distinguishing feature, and what you see is that in a cavity, you actually get the results that you might have expected from your intuition, in the sense that if you take the monochromatic limit, as sigma goes to 0, that's when the probability is maximum. So in these 2 plots where I vary the interaction time versus varying the length of the cavity, what you see is that in both cases, it is true that as you make sigma goes to 0, the probability is maximized. And in particular, they are not 0. And this is really something that is different from the continuum limit. And I should also make a comment that this result, of course, this too is saying that the probability does increase with longer interaction time, and it decreases with inverse proportion to cavity size. So the moral of the story is that the detector field interaction in a cavity and free space are really qualitatively quite different, because one of them depends on space-time dimension, and there is this kind of transparency behavior as you make them more monochromatic, while in a cavity, the behavior I showed in the previous slide is basically true in arbitrary dimension up to like the numerical, like the actual magnitude. And these results are robust against the following modifications. So you might think that it is because we take point-like detector, so a point-like detector is too small to catch everything. And the answer is that that's not true, because you can actually do an exact calculation and show that if you put a spatial smearing on the detector, this point-like limit is actually an upper bound for the transition probability. And this is also true for finite interaction time. That means the behavior as sigma goes to 0 still holds when t is finite, even though it's also true that as you increase t, the probability is bigger for fixed sigma. Now, this is also nothing to do with energy content of the field, because in the limit sigma goes to 0, the total expectation value of the Hamiltonian of the field is actually going to go to the h bar omega that is associated to a typical one particle Fock state. So this disappearance of the probability has nothing to do with the fact that the energy is gone, but it may actually be related to the fact that the energy density, the renormalized stress energy tensor, the 0,0 component does go to 0 because it scales with inverse of the volume. So for cavity, it does not go to 0 because the cavity has finite volume. And this is really quite surprising when you put cavity and free space results side by side, right? Because most of the time, people do this separately, and people don't see this comparison right at when you put them together. To close this talk, I will briefly take you into the realm where there are 2 particle Fock state and the quadratic, and there is the coupling is quadratic that I showed very early in the slides. And there are some interesting things that happens here too, on top of the phenomenon I explained earlier. So for example, if you define two particle Fock state analogously with the previous discussion, where you choose the peaks to the wave packet to essentially have two peaks to make the analysis simpler, and you can argue, you can check that it is indeed the eigenstate of the number operator with eigenvalue 2, and that's why it's a number is a two particle Fock state. And what you notice is that if you redo the same thing but with quadratic coupling, what you realize is that interestingly, you do get the stuff you see in a nonlinear quantum optics. So for example, there will be peaks in the excitation probability that is at the sum of the two peak frequencies. And there's also one more peak that is at the difference of the two frequencies. And this is commonly known as either the sum frequency generation, and in the special case where these two frequencies are equal, this is the second harmonic generation. And the other one is what we call the difference frequency generation, which I tried to find out, and it turns out to be basically what some people call the parametric down conversion.
5 minutes warning, Erickson.
Yep, and I'm done. So what did we talk about? We have talked about how Unruh-Dewitt detectors and its quadratic variant interact with Fock wave packets, and how the cavity walls influence the detector response to these wave packets. And really what we learn is basically the following message: is the cavity QFT, if you put it side by side with a continuum one, when there is a detector, the answer is quite different. And you can see non-linear optical effect that is simply obtained by promoting the coupling to a higher order in the field. And that's it.
All right, thank you very much, Erickson. As usual, if there are questions, please use the raise hand feature, or again, if you can't find it, wave your hands and Rick will see it. So first question, Rob.
Yeah, thanks, Erickson.
Yep.
So yeah, I have a couple of questions. One is, I guess, go back to the thing, like the slide before this. Yeah. So no. You, the one with all the graphs.
This one?
Yeah. So what I'm trying to understand, so how much does this care about quadratic coupling? Would you get similar results if it were linear coupling and two particles?
No. So for linear coupling, right, which I don't show here because of time constraint, what you will get is that you will get peaks at each frequencies. So for linearly coupled detector with two particle Fock states, the resonance will happen at each peak of the Fock wave packet. So this is strictly a quadratic thing.
So this really cares about the non-linear coupling to the detector, basically, right?
Exactly. And this is one way to think. So this is actually a simple way to see why in quantum optics, right, the second harmonic generation and parametric down conversion needs non-linear medium.
Yeah, okay. And the other question I wondered, you looked at free space and a cavity, which is basically a mirror with two walls, right?
Mirror with
a double mirror situation.
Yes.
Is that right? What if you just have one mirror? What will happen?
This is something that I haven't checked before, but our understanding right now is that this difference really boils down to the fact that one of the spectrum is discrete versus one of the spectrum is a continuum. So if you put one mirror, you essentially already discretize the spectrum of the moment at the momentum space already. So I think this will happen the same way as a cavity, although possibly with a different behavior. But we didn't check explicitly for this particular case.
Well, I guess I'm wondering if you're going to get something in between, or if it'll still be like the cavity, right? I mean, it might be an interesting thing to think about.
Right. For example, it is also not obvious, right, that if you consider instead periodic or Neumann boundary conditions, right, the modes are also discrete, but maybe now the fields can run around, right? So
yeah,
so that's also something interesting to look into.
Yeah. Okay, thanks.
Right. Thank you, Rob. We have two questions. One is Rick that can't raise his hand, so he asked me privately, and then Benito. So Rick, why don't you go first?
Yeah, Erickson, can you go back to the 4-plot picture? I mean, that has mine. Yeah, the 4 plots with the free field. Yeah, that's the one, the resonance ones. So I'd like to ask you regarding the physical interpretation of this difference, actually. So what makes like, if you increase the dimensions, you see the behavior of the probability completely changing, right? Going to 0 larger than or equal to 3, and then peaking at this constant thing and n equals 2, and then increasing it at n equals 1. So I'd like to ask you if you have any physical interpretation as to why increasing the dimension affects the field in this way, or the behavior of the resonance effect in this way.
So I think I do have an answer that convinces myself, but I'm not sure if this convinces people, right? So for example, one thing that seems to me a natural explanation for this is that it's like sigma has units, right? But so are the Weichmann functions, and the Weichmann function scales different power laws in different dimensions, right? So the way fields behave and the Fock wave packet spreads around as you change sigma, cares about space-time dimension, because in momentum space, the Weichmann functions cares about these things. So I think that's the mathematical straightforward thing that I think convinces me, but I'm not sure if that's the answer you're looking for.
So if I may make a comment there, so there's the one that convinces me for this, and I think is relevant to that, is kind of interesting, because we say when you consider a wave packet to be more monochromatic, it's obviously going to be more delocalized in space, and the more delocalized in space it becomes is a function of the dimensions of space-time. What is interesting here is that you can also make your detector scale if you want. You can even make your detector not be point-like and scale with the same speed if you want, or with the same speed, scale to cover even the whole space if you want, right? Make the detector completely localized, even if it's unphysical. The interesting thing that the bound that Ericsson talks about tells us is that the fact in which the energy density goes to 0 when you increase sigma, when you decrease sigma, when you make the wave packet more monochromatic, is faster. That cannot be compensated by making the detector bigger. So no matter how big you make your detector, the delocalization effect that dilutes the energy all over space is faster. That's kind of what I feel I learned from that.
Yeah, so one way to think about this is that if you think of this as tied to energy density kind of problem, right, then essentially it boils down to the fact that volume scales faster in higher dimensions. So that's another way to
in this case, I enjoyed Rob Mann's question even more, because then the half mirror space-time, right? The 1 mirror space-time, then that actually would be able to answer the question whether or not there's an effect related to the discrete spectrum or to the delocalization in space-time associated to the wave functions, right? To the
exactly
particles.
Up to the fact that picking a Gaussian in these cases is a little bit tricky, because the Gaussian has to stop at the mirrors and you have to do some stitching. But maybe with some compactly supported one, you can do something about it. But you are right. The reason why some of these things are a little bit complicated is that if you cut a space into half, then some of these choices have to be made a little bit more carefully. But that's definitely an interesting way to look into whether the real culprit is discrete versus continuum, or something else is coming.
I'm very interested in that, actually. Well, yes, okay. Thank you so much.
Thank you. The next question is Benito.
Hello.
Yep.
Okay, maybe I'm even gonna turn on my camera.
Nice.
Also, so always a mess in the morning, the house. So I think my question was already more or less answered in Rob Mann's question, because I was just wondering about the role of boundary conditions. I mean, you use this kind of perfect mirrors, but you can choose whatever you like, and maybe also interesting to think of transparent boundary conditions, because
exactly like the Neumann boundary condition, mixed boundary conditions, you can consider.
Yeah, exactly. Things. So my comment was in that direction. I mean, it's even between two boxes with different boundary conditions, you expect very different behavior for responses, probabilities, and whatnot. So it was just a comment in that direction that
right.
might be interesting to explore.
There's also something else, right? For example, in scalar fields, right, there is no notion of transverse boundary condition, in the sense that, for example, if you put a Neumann boundary condition, but you have electromagnetic field instead, right, you can kill off the magnetic field part, but there is no magnetic part of the field. So maybe there is something else that can play around with those things too. So the fact that, for example, in Jorma also have done a lot of calculations using Dirac spinors, right? So whether spin actually matters also. So it's like these calculations already kind of brings more questions than the answers, right? Because now you are now being now you can see that you're gonna end up asking who are the real culprits. Is it really this thing, right? So yeah, so basically this can be a starting point to chasing the culprit, really.
Yeah. And a little comment on the question with a single boundary condition, a single mirror instead of two. So half space or something like that. I mean, in that case, I think that one way of thinking about this is that really when you act with this, so you have very well explained that, you know, this annihilation and creation and annihilation operators are not really sharp. So you have to smear them against some test function in momentum space and so on. This is really correct way of thinking about this. But also another way of thinking about this issue with how these operators act is that you can smear them against solutions. So solutions of the
Right.
Klein-Gordon equation. And then in that sense, you have these very natural candidates for what kind of smearing to use in the single boundary case, because basically you just have to put in a solution of the Klein-Gordon equation in half space with the right boundary condition that you're interested in.
Exactly.
And then you don't have to kill yourself thinking about how to cut off a Gaussian or something.
Right, exactly.
Because, I think that you can do it like that.
Yeah, that's a very good interpretation, right? Because now you basically shift the smearing into, since the smearing is a matter of interaction, you just push it to the field, and the field just treat the smearing as something that solves the boundary condition in the Klein-Gordon equation.
Yeah, that's right. Okay, that was it. Okay, thank you. It was a very nice talk.
Oh, thank you.
Very nice questions too, Benito. Very good. Next person is Cisco.
Hello. Yes, I just had. It wasn't exactly clear to me what the implications were as you go from these cavity modes to the continuum, for whether the detector thermalizes or whether the response appears thermal in some sense. Could you comment on that?
Right. So one thing I can comment first is that at least the way I present it here cannot answer that question, right? Because my detector is inertial. So that means I'm not
okay. So none of these. Okay. None of these situations involved acceleration. This was just to set up the smearing and the discretization.
That's right.
Okay.
Although the nice thing about this thing is that since everyone knows in Unruh-Lewis model that you can simply make things accelerate, so you can just change the trajectories into an accelerating trajectory, although you have to cut it off once it gets out of cavity, right, and make comparisons. But essentially, up to the fact that you can change the trajectory, you probably can answer that question to some extent.
Okay.
Okay, sorry. I have a comment about that. You can already predict what's going to happen if you have a 4-wave packet and you consider detector accelerating, right? With enough time, the wave packet or anything that is not Lorentz invariant in the state of the field, the only state of the field that's Lorentz invariant is the vacuum. So every excitation that's not going to be Lorentz invariant, like this wave packet, would be red-shifted and blue-shifted away from the response of the detector, and eventually the detector will thermalize to the Unruh temperature, no matter what state you put in the field. The only thing that will survive this extreme redshift and blue shift would be the vacuum, and therefore you would see the Unruh temperature. That'll be my guess to any excitation of the field, actually.
Yeah, but you cannot compare this with a cavity because you're going to get cut off by the size of the cavity.
Oh, sorry, so I'm talking free space, of course.
Yeah. Presumably, it would. That statement might be able to apply inside a cavity if you had a big enough cavity compared to how long you've been.
Exactly. Yeah.
Okay. Thank you.
Are there more questions? If there aren't any, I'm gonna ask one. Well, I guess two. One is a comment. So Erickson, if you can go to the beginning of the talk, the very beginning. I feel bad. I comment because I feel bad myself. I want to say, you cited, there.
Yeah.
No, go forward.
Yeah.
We'll have the citations. There we go. So in this slide, can you show the whole slide? Yes, a disclaimer, right? I mean, you cite me here, and I feel bad because certainly these things are not known since 2016 because I did them. It says the whole from the time of Andrew and DeWitt, and then Takagi and etc., Jorma and many other people. So just
yeah. But I picked the one that fits the notation also, right? Because I think by now, if I say Unruh DeWitt detector, then everyone should know that it comes from Unruh and DeWitt, for example.
I just feel compelled to say because I felt with that. The real question that I have is, maybe you can make a comment about, because something common to do in quantum optics, and maybe sometimes even in basic QFT, is to talk about canonical quantization and do things in finite volumes, right? And then consider even wave packets in cavities, and then take the limit of infinitely long cavities, and then recover the continuum theory. But you seem to be pointing out that in terms of responses of detectors, those limits may not commute, no? And maybe you can talk a little bit about that.
Yeah, so essentially what happens is that if you do a standard canonical quantization and then do all those Bogolubov calculations, right, you only have the field, you don't have the detector, right? So taking the limit basically, even though in a cavity the Hilbert space is quite different from the Hilbert space of the continuum, taking the limit, since that's the only thing you are involved in, so taking the limit is fine. But once you put in the detector cares about what's the Hilbert space of the field. Essentially, what happens is that, as you see in the calculation involving the cavity, right, or even here, right, what happens is that in this kind of calculation, like what Benito was saying, essentially in free space you have to smear the creation and annihilation operator, but in cavity mathematically it is well defined to have a sharp A and A daggers. So the fact that these two things are different when you couple a detector in means that really when you want to think about the problem involving like matter interaction, you really have to care, you have to really think about this non-commuting between putting a detector and take the large cavity limit and vice versa. Essentially, the moral of the story is that once you put a detector in, right, you have to be careful about just saying that, free space is just a big cavity. So essentially, that's the thing, right?
Right. Thank you very much. Are there any final questions? I don't see any more. But if not, let's thank Ericsson again. Thank you very much. And we're going to go to our next speaker. So I'm going to stop the recording now. All right. So our next speaker is Nikos Kolas. Nikolaos Kolas. Sorry about the pronunciation, probably butchered it. He's going to talk about assisted harvesting and, wow, catalysis of coherence from scalar fields. That's going to be cool. All right. From the University of Patras. The floor is yours. Go ahead.
Hello, thank you very much. So this is a project that I've been collaborating with Dimitris Moustos on the group of relativistic quantum information and foundations at the University of Patras. So let me start explaining what quantum coherence is. So quantum coherence is a non-classical phenomenon which allows a system to exist simultaneously in two different states. And Feynman famously said that this phenomenon lies at the very heart of quantum mechanics. So what are the applications of coherence? Coherence is pretty much the basis for much of quantum computation. So, for example, when you take the Hadamard gate and you act this on the computational basis, what you actually do is you bring the qubit into superposition of equal probability between its computational bases. Coherence also plays a key role in processes like biology and thermodynamics. So coherence lies at the heart of many different quantum phenomena. So a very famous example of a coherent state is the Schrödinger cat. So in Schrödinger's thought experiment, you have a cat that has a 50% chance of being alive and a 50% chance of being dead when it's inside a box. But in theory, you could have a case where you have a cat that the chances of it being dead or alive are different. You could have a cat that has like a 70% chance of being alive and a 30% chance of being dead, or 90% chance of being alive and a 10% chance of being dead. So what coherence shows you, but the situation which is furthest away from our classical intuition is a cat which is at the same time both dead and alive. And what coherence shows you, it actually quantifies this non-classicality. So if you try and measure coherence in the basis of the cat which is both dead and alive, a simple way of calculating the coherence of such a state is you, by simply multiplying the probabilities and just multiply the probabilities and multiply by 2. So you see a cat which is both dead and alive with the same probability has a coherence measure 1. One that has a 60% chance of being alive and a 40% chance of being dead has a coherence measure of 0.98. And the more classical the state gets, so the bigger that the probability is now being one state or the other, the amount of coherence goes down. So the more classical the state is, the less coherence it has, and the more quantum the state is, the more coherence it has. So this is just an example. So mathematically, what is coherence? Coherence is a base-dependent quantity, so you have to define a basis into which to measure coherence. So what you do is you just write your state in the basis that you've chosen, and coherence tells you the amount of non-diagonality of the state. So for a state that is completely diagonal with respect to this basis, it's called incoherent. You say it doesn't have any coherence at all. While if it has even a single element, a single non-diagonal element, then you call it a coherent state. And a way of measuring the coherence of a state is by simply taking the modulus of its non-diagonal elements and summing over all of these non-zero terms. So now I'm going to talk about assisted coherence harvesting. So coherence harvesting is works pretty much the same way that entanglement harvesting does. So you have unriddled bit detectors, which is a 2-level system with 2 energy levels separated by an energy gap omega. So initially your qubit is in the ground state. And then what you do is you interact this detector with a scalar quantum field through a derivative coupling with a field. So assuming that at some point you turn on the interaction, some initial time, after you've turned off the interaction, the qubit, depending on the state of the field, will find itself in a superposition of its 2 energy levels. So in this way, you've harvested an amount of coherence between these energy levels. The only difference is that this needs this is an energy consuming process, and because a flow of energy is always associated with an external increase of the coherence of the combined system, this is the reason we've called this as an assisted protocol and not an actual coherence harvesting protocol. So the difference with an entanglement protocol is that you actually harvest in entanglement harvesting, you actually harvest entanglement from the vacuum, from the field. But in this case, you harvest part of the coherence from the field, but part of the coherence has come outside just because you've invested some energy in order to carry out this harvesting process. So a little bit of detail about the interaction. So this is the derivative interaction. So lambda is just a coupling constant. X is the switching function, which tells you the way that you turn on and off the interactions, the interaction. U is just the monopole operator of the qubit, and phi is just, we use the smeared field version of the field, just so we can model in an extended qubit, a qubit that has size. We're only going to consider normalized smearing and switching functions. There's 2 reasons why we do this. One reason is that we'd like to, in the future, compare different what the effects of different smearing and switching functions. What are their effects on coherence harvesting? And the other reason we do this is so we can take the limit of a point-like detector where the smearing function would be a delta function, and a instantaneous interaction, so a qubit that interacts only at a single time with the field. So that would be the limit where the switching function is a delta function as well. So it turns out for a detector initially in a ground state, the amount of coherence that you harvest by using the L1 norm of coherence that I showed in the previous slide to the lowest order is just given by 2 times the expectation value of this operator, this field operator. So what we found is that that for delta interaction, so for the instantaneous interaction, when the qubit interacts instantaneously with the field, coherence is catalytic. So what does this mean? This means that after you've extracted some coherence, you can use the field again. The state of the field has changed, but you can use it again to extract the same amount of coherence over and over and over again. And this is a repeatable process, and you can repeat it for as many times as you like. The only thing is that this has a cost in energy, so you're actually bounded by how much energy you could actually invest in harvesting. So our first result is this, that for an instantaneous interaction for a switching function versus a delta function, coherence is catalytic. So just for an example, I'll show you now what happens when you try and harvest coherence from a coherent state of the field. So coherent state of the field is defined such that when the annihilation operator acts on the state of the field, a coherent state is actually the eigenvector of annihilation operator with an eigenvalue alpha kappa, where alpha is just a coherent state amplitude distribution. So in order to demonstrate, we've assumed that the smearing, the switching, and the amplitude distribution are all given by Gaussians. We just did this so we can make so our equations can be analytically treated. And just notice that the amplitude distribution has an extra phase. I'll talk about this a bit later. So our parameters here, we have three parameters here to consider. We have the mean interaction duration, so how long does the qubit interact with the field. We have the mean radius, so what is the actual size of the qubit. But we will consider that, for our example, we'll consider that the radius of the qubit is approximately equal to 1 over omega. So, and the third parameter is the mean initial field energy. So here you can see what is the amount of harvested coherence for a detector which is not moving, so it is static. So we have two cases. When the phase of the coherent amplitude distribution is equal to 90 degrees, what you see is that for a very short interaction duration, you can harvest the maximum amount of coherence. And the longer you allow the qubit to interact with the field, the amount of coherence that can be extracted gets less and less. The other thing that you can see is that when the initial energy of the field is equal to the energy of the qubit, you can allow the qubit to interact for a longer period of time with the field and still extracts a small amount of coherence. In the case where the phase of the coherent field distribution is equal to 0, then this changes a bit the profile of the harvesting protocol. So now for initial time of t equals 0, you can't get any coherence at all. You get a bigger value for times that are equal to 1 over omega. So this changes a bit where you get the maximum amount of extractable coherence, but qualitatively, you still find that the longer that you allow the qubit to interact with the field, the less amount of coherence you get. And when the energy of the field is the same as that of the qubit, then compared to other energies, you can allow the qubit to interact longer with the field. So these are, this is the same, this is the amount of harvested coherence, but now this is for a qubit which is moving with a constant speed equal to about 0.6 of that of the speed of light. So this changes a bit the harvesting profile. Qualitatively, you still find the same results, that the longer you let the qubit interact with the field, the less amount of coherence that you can extract. So in the right diagram, we've compared the amount of coherence extracted for a moving qubit with a speed of 0.6 compared to that when it's not moving. And what you can see is that these are the regions where for a moving detector, you can extract more coherence than from a detector that is static. So these two regions, the one down here and the one over here, are the ones where you can extract more coherence for a moving detector. And in this region where, let's say that the energy of the field is of the same order as that of the qubit, a static detector can extract more coherence from the field than when it is moving. And this is the same results, but now for a coherent amplitude distribution without a phase. But so again, you have this region where when the energy of the field is exactly the same as that of the qubit, you get harvesting from an initial detector is more efficient than harvesting from a moving detector. While in these two regions, a moving detector can actually harvest more coherence than a static one. So in the final slide, what you see here is the energy cost of catalysis. So if you remember what I said previously is if you have a switching function that is equal to a delta function, so for a particle that interacts with a qubit instantaneously, you can get, you have catalysis. So what this means is that depending on the initial energy of the field, every time you try to extract coherence, you will get exactly the same amount of coherence. So, and this is repeatable. So what I've drawn here is this is the amount of coherence that you can extract. And the second curve here is the amount of energy cost that is needed, that you need to invest in order to extract coherence. So what you see, there's a slight correlation. So when you can extract the maximum amount of coherence, you need to invest a maximum amount of energy in order to do this. Yeah. So the conclusions, what we saw is that for a delta function, coherence is catalytic. You can repeat the process as many times as you like. The other conclusion is that the phase of the coherent amplitude distribution affects harvesting. Also, when the initial energy of the field is the same order as that of the qubit, a static detector is able to harvest more coherence than when it is moving. For different energy, for different initial energies of the field, this situation is reversed, is changed. And finally, coherence harvesting in the derivative coupling is an energy-consuming process. So when you're harvesting coherence, you have to take into consideration that this is an energy-consuming process, and you need to invest some energy in order to do this. So thank you very much.
All right. Thank you very much for your talk. Again, as usual, questions we handle the usual way. Use the raise hand feature. And Rob, you have the first question.
Yeah, thanks. That's a very interesting talk. I'm just trying to understand the setup here. Is this a single detector interacting with a field that ultimately becomes superposed, or are there two?
Yes, this is a single detector. You just do it once at a time. So you put a single detector in, you make it interact with the field, and you after you switch off the interaction, it's superposed. And then you can repeat the process with a second qubit, a third qubit, and so on, and so on.
Right. But I mean, it's not okay. So yeah, so it's really the whole thing. I thought it was entanglement based on the title.
No, it's coherence. So this is like a different kind of resource. The two main resources in quantum information theory are entanglement and coherence.
I would have called it superposition harvesting, but I think probably coherence harvesting is a better.
This is a standard terminology in what's called resource theories.
Yeah, I see. So it's a way of getting, in some sense, this is a method of getting a UDW to be in superposition, correct?
Exactly. Yes, exactly.
Yeah. So two other things. One is, how do you measure the energy of the field? And the other is, can you put the detector in different motion like stationary and moving, or back to back, or some such thing?
Okay, so maybe I didn't explain it very well. I didn't actually measure the energy of the field. It's the energy difference. And it's the total energy difference. You measure the final energy of the field and the detector, and you subtract that from that, the initial energy of the field and the detector. So what I'm interested in is in the energy cost, how much extra energy you need to invest in order to harvest.
Okay, so that E is that energy difference.
It's the energy difference. Yeah, I'm very sorry. I didn't explain that very well. Yeah. But we haven't considered like superpositions of motion or different. Yeah, we haven't considered different superpositions of positions, because this is this is just.
Yeah, it's the superposition of energy levels, but it'd be interesting if this could be somehow generalized to superpositions of detector motion or something.
Yeah. Well, this is in the we plan in the future to look at all these different things that we could do.
Yeah.
But this is brand new. I mean, I don't correct me if I'm wrong, but from what I'm aware, this is like the first time that somebody's looked into coherence in these settings. So
Yeah,
you know,
I think you're right. Yeah.
So this is brand new. We're still, trying to understand what's going on, and then we're exploring different things as well.
Okay, thank you.
You're welcome.
Right. Are there any more questions? I do have questions.
Yes.
So one is related to Rob's question. I had it like I was actually about to suggest you could consider the dynamics of the center of mass of the detector. And once you have the dynamics of the center of mass of the detector in, how the field delocalizes detectors, that is a very fundamental. So I know that you're looking at it from the point of view of let's produce coherence because it's a resource, right? That's what you take and that's what you want.
Yes.
But there's a very interesting fundamental question, which is the interaction with the field localizing atoms and localizing systems? And it does, or delocalizing even, right? Under what conditions interaction with the field would generate coherence, for example, in the center of mass Hilbert space, if you want. In the basis of positions of where you put the detector, right? You would expect that would happen too, very likely, right? If you, I mean, at least a priori, if you consider,
Yeah, but the problem with coherence is that it's very easy to measure coherence when you're talking about two levels when your space is discrete. So in this case, it's very easy to find a measure of coherence because this is what you have to find something to measure with. So I'm not aware. I don't think that there are any measures right now for continuous variables. This is a problem that hasn't been solved in the.
I guess I was looking at it from the point of view not of resource, but rather how does the interaction with the field delocalizes, if any, the detector can delocalize even in the optimal way. Maybe there's protocols that or localize or delocalize. How the coherence in the center of mass degree of freedom in a particular basis, which is the position basis, if you want. Is affected, and I guess that could be an interesting question to answer.
Yeah, as I said previously, we have a lot of open questions that we'd like to look into the future. So maybe that's one that we could either talk about or we could consider. Yes.
Right. There is a more technical, I guess, question I have. So you use two things that are less standard. Well, less standard. They are standard, but in not the way you use them. You use two things. You use a derivative coupling.
Yes, exactly.
You also use kind of nascent delta family of switchings that have units, right? So the one thing that is, if you can go to not the delta case, but the case in general, when you consider a Gaussian, I forgot what it was. You can show me the switching function that you use. Right. The one thing that I would argue with that is that usually in the way you do, of course, when we do delta switching, certainly there's an extra scale, right? Usually in Android detectors, the switching functions are dimensionless. There's a reason for that, right? Because the mirroring function has to be dimension full. It's inside an integral over space. The switching function is dimensionless. So when you are comparing different T's, different capital T's here, you are kind of affecting the coupling strength.
I've just changed the dimensions of the coupling.
That's right. That's right. So you change the dimensions of the coupling, and the one that reproduces. So one comment again that is just. To compare unequal footing, for example, if you do the analog with what would be atomic physics, right? If you say, I'm using the Andrew weight as an approximation for what would be a system in atomic physics, and my switching function is given by some preparation process, or maybe putting the atom in a Faraday cage or whatever, something like that. In those cases, you do not change the dimensionality of the coupling associated with it would be not the right one if you actually consider this kind of nascent delta coupling. So I guess I'm not saying it's wrong or anything, not at all. It's just something to keep in mind. I think that when you compare unequal footing these things, you are including the scale in the strength of the coupling. That scale of duration is included in the strength of the coupling.
Yeah, I understand it. Yes, but one of the reasons we chose the derivative coupling is so we can make our results closer to a real case where you'd have a qubit interactive electromagnetic field. One reason is this, and the other reason is that we wanted to avoid IR divergence issues, which are usually associated with the inter-dividend interaction. And the other reason we chose this switching function is that so you could compare this with like let's say a pulse electromagnetic field, a pulsed electromagnetic field interacting with a qubit. So we think this is a bit more physical, maybe.
I would disagree with that, but then again, we can talk offline about that. Also, there's some literature I can send you about which one matches more closely the light matter interaction, like the full electromagnetic interaction, the derivative coupling or the non-derivative coupling. Because of course, first thought is like, oh yeah, if you couple to E, that's kind of a derivative. So maybe that matches better. Actually not, it's the non-derivative one that matches closely.
Yes, I know about well, as I said previously, one of the reasons we chose this coupling is so we could avoid IR divergence issues.
Right. No, that's for sure.
This is just like the example I showed you was the 3 + 1 dimension, so 3-dimensional space. But we've done the same thing for a 1-dimensional space as well. And if you don't do this with a derivative coupling, then you have issues with the derivative coupling. You get like what happens is your coherence cannot be greater than 1. You see, but if you don't do this, if you do this with the uniderivative coupling, then you get coherences that are not physical.
So what do you mean by not physical?
you would actually get coherences that would exceed the number that you know you can't exceed. You see.
Right. So the one thing that if you were not normalizing, say the switching, and you do 1 + 1D with derivative coupling, the scaling and so on mimics the 3 + 1D without derivative coupling. Now, of course, you could have done the derivative coupling, the non-derivative coupling 1 + 1D and put an artificial IR cutoff, right? And you would have gotten something.
Yes, I know that. Yes. But we just want to avoid all of those issues. All of those issues. That's why we chose the derivative coupling.
It's just a little bit of the subtleties, I guess, to mention in the choice of the model, which I think the results are definitely qualitatively very interesting. But the devil is in the details of the choice of the model. How much you want to resemble. Yes.
I mean, if you change the switching function and you make it like a sudden switching, like a previous in the previous talk, then your results would change. But this depends on what kind of profile you want for the switching. If you want it to look more like a pulse, maybe, or if you want like an interaction that's turned on all the time. So depending on the situation, the results will change. But it's different physical situations, you see. So it's
definitely. I think that's it. I mean, that's something that to discuss. I think that we can discuss these things offline too, but because there's a lot of things. I enjoyed the talk very much. Very good talk.
Thank you very much.
Does anybody have any more questions before we do the closing of the session, I guess? All right. Okay, there are more questions. Then let's thank Nikos again. And please let's thank all the speakers of the session. Been great talks in this session. Thank you very much. All right, so with this, this is the end of this 5th session. Remember 2 things. There's going to be an the last Australian session will happen this evening for Waterloo. That will happen at 7 p.m. EST. So please adjust to your own time zone. And remember that we have another session exactly like this one, the 6th one, next week at the same time. And remember that these sessions are going to continue up until May. Everybody has been scheduled. So we know exactly how long all the sessions are going to take. We're going to have it at the beginning of May. That will be the last session. Also, finally, remember that there will be all these talks, as well as the Australian ones when we get them from them, are posted on at least for now, temporarily, on the YouTube link that was sent in your email reminders. So you can also watch and go back and see them, or tell anybody that hasn't come to see them. Other than that, again, thank you very much to everyone for coming, and I'll see you next week. Thank you. Thank you.